I so oh, there is a new homework posted, but and I think we'll get to probably get to notes on that homework. I just put a due date on this just to get it on the calendar, but we may have to adjust that. But to due today is finally that homework on integration, right? Okay, with natural logs. So it looked like as of this morning, at least about 2/3 of the class were working on it, and they had done pretty substantial progress because the median score was high, and so that's good. But then a few of you are still, need to finish that, right? So you want to, of course, get that done by midnight, right? So you can keep that nice homework average that you established with the first homework. That first homework that's not posted there, the 5.1 homework, you can still find that. I think if you go to past assignments, and I have posted I turned on the answer key to that. So if you open that homework now, it's going to show the answer key. So if there was any questions that you couldn't do, or you couldn't get WebAssign to grade it properly, you can look at the answer key now, and I think compare it with what you had typed in as the answer. If you put an answer to the question, it doesn't show you solutions, but it's just the key is filled in. So as soon as we get past, I'll try to remember to do that as soon as we get past the extension period, right? Turn on the answer key. And that's important for these homeworks, right? Because we have a test coming up in a couple of weeks, right? Okay. 2 weeks from today, actually. Exactly. On February the 19th. Now, having said that, we have now posted. Oh, there was an announcement to this effect over on WebAssign. So if you were glancing over there on the right-hand side of the page, you saw that announcement. The sample test is posted. So if you go to the Blackboard page, that's in the Blackboard page, not a WebAssign, and go to where it says sample test here, just click on that link, and that's the folder that has the sample test. So the first sample test is there. Okay. So you can open that and print that and be working on that. This gives you a preview, not a preview, but an idea of what the format of the test is going to be, okay? And what sort of questions might be on the test, and how I construct tests. So the problems are, of course, going to look a lot like the homework problems, very similar to the homework problems. There should be very little by the time you take the test that's a surprise to you. Now, if you look at it now, there's going to be some things that are new because we haven't covered everything that we're going to cover up until the time of the test, right? But a lot of it, of course, you're already familiar with. So you can start working on the sample test. Now, however, the big difference between this and the test is, the problems will be different. So don't think that memorizing the answers here is going to help you on the test. Okay, they're completely different questions. And this is longer. So when you open this and it looks long, then don't get too freaked out, right? It's long. It's designed to be longer, just so we can have lots of different questions of different types, right? But the test will fit into the time frame, all right? So that you're allotted, which is whatever our time is here, 9:45 minutes. So you'll have time to take the test. Of course, if you're prepared for the test, right? So there it is. So now I think it's really important that you do take the time to go through the sample test, right? Work on the sample test prior to taking the test. That will really help you prepare for the test. But of course, you've also got your homework to finish. So things are going to be getting busier here, right, as we approach this first test, okay? Because you want to be working on the sample test in addition to your homework. In addition to those, right, that optional homework, that one optional homework, right, on inverse functions, if you want to do that. Don't forget the calculus review. That's not an optional homework, but that's due at the time of the test. So anyway, yeah. So the pace here is going to pick up a little bit around the first test, and then it'll get relax a little bit after the first test, and then again start accelerating as we as we get closer to the second midterm, right? Okay, now I will post the answers eventually, but not immediately, because I want you to work on the test independent of having the solutions in front of you. So I want you to give the test a try. Do your best you can on the problems. Look at the notes, the corresponding class notes for a particular type of problem. Go to the Math Center and ask questions about a problem. Taylor will help you with the sample test, and I think that will be part of Taylor's test review. Do you think about a day for that?
It'll be that Monday.
The Monday prior to the test, yeah. So Taylor will have a formal test review the Monday prior to that test, which is what, the 17th? Yeah, on the 17th. So I guess the time will be.
Yeah, I haven't.
Yeah, so we'll set a time, but anyway, it'll be on that Monday. So that's another place to get help. But eventually I will post the solutions, but I'm not in a rush to do that because I want you to work on this before you before you look at the answers. Okay. Because I always have to warn students about this. It's not effective studying for the test. It's not effective to use the test review by looking at the problem on the test review and then looking at the solution to the problem and saying, oh yeah, I understand how that solution came about. Okay, that's not effective way of studying. You have to try to come up with the solution yourself, struggle with it a little bit, right? Or maybe a lot, okay? You have to try it first. Then, if you cannot finish it, or once you finish it, if you want to check your work, then go back and look at the solutions. But don't say, oh, I see this problem, I see the solutions, oh yeah, I see how that solution was done. That's not going to get it done for the test. You won't be able to reproduce that sort of problem on the test if you do that, okay? So that's my word of advice. But the worst thing to do is to not look at the sample test at all. All right. Some of you, okay, are going to misbehave, right? And you're not going to look at the sample test, okay? So I understand that, and that you will pay a price for that, okay? So that's going to impact your grade. But it is your grade, okay? You won't make that mistake twice, I hope, okay? But some of you will the first time, and you'll learn from that mistake, and you won't do that again, okay? So it'd be better just to avoid that situation altogether. It really does help, okay, of course, preparing for all the tests is important, but the test number one is a particularly crucial one, because what happens is if you don't do well on that test, then your anxiety level just really goes high, okay? And then you really feel pressured for the second test. I've got to do good on the second test now, right? And that detracts from your performance. That anxiety is going to detract from your performance. So if you do well on the first test, you'll feel a lot more relaxed. You don't want to slack off, but you'll feel much less anxiety going into the second test, right? And that will help you, okay? Also, if you do well on test number one, you will know, oh, I'm capable of doing this. I'm capable of preparing for the test. I know what I need to do to, do well on the test, okay? All right, so, those are just general college success tips, right? Not unique to this class. All right, so you can print that, right? Okay, so don't wait too long to start looking at that. But first things first, you got to finish your homework for tonight. Do y'all have questions about tonight's homework so far? Yes. Is that a question? Yes. Mm-hmm. Okay. So, all right. So let me see if I can do this. All right. So y'all may have to help me. That one's hard. The answer's awkward in WebAssign or wrong in WebAssign? It's just awkward. Okay, all right. Okay, let me see that one. So, boy, there's, well, that's a pretty typical Calculus 2 question. That is the typical Calculus 2 question. I mean, I think 80% of our questions are going to look like that. Maybe that's a high percentage, but pretty close to that. It's just going to say, find the indefinite integral, right? Find the antiderivative of this expression. So it's 2x squared plus 4x minus 2 over x minus 6, okay? All right, so we have to, so when we're facing an antiderivative like this, right, we just have to reach into our anti-differentiation bag of tricks, right, and think about what techniques does it look like we can apply to that problem, right, okay? And sometimes that's a trial and error process, or sometimes you're going to see it instantly. And I try to give you clues, right, on sort of the form of the integrand, the form of the expression you're integrating. You can pick up clues from that, right, as to what technique you want to try here. Okay, so what did you think about in terms of finding that antiderivative in number 6? What sort of method were you thinking of?
First I took out the u, and then I did the d over dx, and I found what dx was equal to, and then I tried to do the long division for...
Oh, you tried to do long division? Yeah, I wanted you to start with long division. I think so you got to it there, but I think the first thing to look at when you see that problem is to think long division. Okay, yeah, think long division. Because why? What's the clue in that integrand that makes you think long division might be helpful? The degree on top is more than the degree of the bottom, right? Yeah, see, those are the sorts of things that we've been talking about, right, that I'm hoping that you'll sort of, recognize quickly, right? You have a rational expression here, right, and the degree on the top is bigger than the degree of the bottom, and that often is a convenient opportunity for long division, okay? So let's try that and see if that's going to work. All right, so do y'all have that written down? Because I'm going to switch to... some paper here. So let's see, what was that? Obviously, antiderivative. I remember the 2x squared here. What was the rest of that? Minus 4x, plus 4x, and then minus 2 over x minus 6. Yeah, now keep in mind, my version of the problem is going to be maybe a little bit different from yours, right, in your homework, okay? Because some of these problems are algorithmically generated, so I get a slightly different version, and you'll get a slightly different version from others, right? All right, so let's try the long division. So I'm going to divide x minus 6, right, into 2x squared plus 4x minus 2, okay? All right, so y'all practiced that process in the past, that in some course, right? Prior to Calculus 2. X goes into 2x squared 2x times, right? And again, don't be shy about writing that down if you need to, right? We're going to divide x into 2x squared. The leading term here divided into the leading term here, right? And of course, that reduces to 2x. That's why I wrote the 2x. Notice I put it above the 4x, right? Don't forget that. You want to keep your terms lined up. That's just going to help you do the work correctly. So that's just kind of an error prevention device there. Let's see. Now let's multiply back through. So 2x times x, of course, is 2x squared. Had to be, right? And then 2x times minus 6 is minus 12x. And now we subtract, right, which is the same as changing the signs and adding. So now I've got 16x, and I can bring down the minus 2. Of course, these two terms are going to disappear, right? X goes into 16x now, plus 16 times, right? Again, write it down if you need to. So 16x divided by x is 16, right? Okay. Now multiply back through again. So, of course, 16 times x is 16x. And then 16 times a minus 6, oh my word, what's that? Minus 96? Yeah, because these problems are algorithmically generated, sometimes you get unusual values in them, okay? Because the computer's generating them, and according to some algorithm, they don't really sometimes care about what sort of numbers come up in the answers. All right, so you change the signs and add again, right? So this is 94 now, right? And that's it, because the remainder here now is 94. That has degree 0. That's a constant. So constants have degree 0. As polynomials, constants have degree 0. But this is degree 1. When the degree of the remainder is less than the degree of the divisor, that's when you can stop the long division. So we're through here, right? Here's our quotient, 2x plus 16. There's the remainder. Now, what do we do with the quotient and remainder? So, well, we're going to use that to rewrite the integrand, right? So I have 2x plus 16, and then take your remainder, right, and divide it by the x minus 6. So these two integrands are the same. I've just written them in a different form, right? And, of course, the dx is still there. Now, at first glance, right, that looks maybe harder than the original problem, but it's really not. Because now we can integrate term by term. So I can integrate this term, and this term separately. So I end up with 3 different integrations to do. That sounds worse than one integration, right? But it's actually easier, because these are all easier integrals to compute, right? What is the antiderivative of 2x? It's 2x squared divided by 2, right, which is x squared, right? So now you're using not the power rule, but the anti-power rule, right, okay, because we're integrating. So you add 1 to the exponent and divide by the new exponent, right? What's the antiderivative of 16? I think we were debating this last time, right? But what's the antiderivative of 16? What? Yeah, 16x, right, okay. That's just 16x. And then plus, now the harder one is the last one, right? We want the antiderivative of 94 over x minus 6. Well, the first thing I notice is I can factor out the numerator, so get that big 94 out of the way. I'm going to put that in front, and then I have the antiderivative of 1 over x minus 6 dx, okay? And so that's the last integration we have to confront. We're done using the long division. Now we have to think about, how am I going to integrate that, and what does that suggest? Yeah, you can use substitution, because we're hoping that ultimately we will be able to integrate this using what? A log, right. Yeah, using natural log, right, because here we have the reciprocal of an expression. Actually, I can avoid using the substitution in this case. This one's kind of simple. All right, so, but you can go ahead and do the substitution. It works fine. Just substitute u for x minus 6. Is that what you did? Did you get to that point?
Yeah, but I saw where I messed up.
Okay, all right. Oh, you didn't do the long division, right?
Nope, yeah, my long division.
Okay, so you can substitute u for x minus 6. So that's fine. That's really the kind of formal way of doing this last, finding this last antiderivative. However, here we get a little bit lucky, because what's the derivative of x minus 6? 1, right, yeah, which is what you have in the numerator here, right, okay? You have in the numerator just 1, because we had a good sense to factor the 94 out, right? So see, here I have an expression divided into its derivative. This is a derivative of an expression over an expression, and we know that always integrates as natural log of the denominator. Whenever you have the whenever you have the derivative of the denominator in the numerator, that's going to integrate using natural log. So we can sort of skip the substitution step there. We don't have to, but in this case we can, because we immediately see, oh, this is going to be 94, and then times the natural log of the absolute value of x minus 6, and then we add on the constant, okay? So, oops, this is 16, right? Okay, so there we go. All right. So that's it, I think. So that, I think when you open the sample test, you can see a problem very similar to this one. This is a very standard long division type problem, okay? So I know you'll have one almost exactly like this on the sample test and also on the test as well. I'll give you hint there about the test. Okay. Okay. So other questions from that homework? 5.2. Yes. Number 8. Okay, all right. So we saw an example like this one last time, right? Okay. I went through the example, right? Yeah. So we do have an example like this one in the notes, but let me get you started at least on this one. And it's just the format of the answer is weird.
Well, I mean, the answer that they gave me, I don't know if they'll take it in a different format, but the format of the answer that I saw, like on my answer key, was awkward.
Oh, okay. All right. I'll look at the. Let me see if I can look at the answer key and see what. You look like you're changing your mind. You.
Oh, me?
Yeah.
Oh, no, it's fine. I don't even remember we did an example last time.
Okay. So, so let's write this one down just to get started. But I'm not going to go through all the gory details. So it's in the notes. There's an example like this one. That means it will be in the video, the lecture video. You'll have to, of course, fast forward, right, to find it. But all right, but let's start it. So it's 1 over 7 plus square root of 2x, right? So let me write that down. So antiderivative of 1 over 7 plus square root of 2x, okay? And so how are we going to attack this? Yeah, I think there's no other way here than just to try substitution. And I think the only thing I can see to substitute for is the denominator here, okay? So, and it's not at all clear when you start that this substitution is going to work at all. So, so we can be a little bit nervous at first here about, is this even going to work, right, making this substitution? But we'll hope for the best. So let's take the derivative of u, right? But before I take the derivative, convert that radical to a fractional exponent. That's pretty standard practice, right, when you want to take a derivative. So we're going to take that square root of x and 2x and write that as 2x to the 1/2 power. Now let's take the derivative. Well, the derivative of 7 is 0 because that's a constant, right? Not the integral of 7. So don't write 7x, right? The derivative of 7 is 0. And what's the derivative of 2x to the 1/2 power? Well, it's 1/2 2x to the minus 1/2 power, right? Because you subtract 1 from the 1/2. So you end up here with 1/2 times 1 over 2x to the 1/2 power, because I can get rid of that minus sign by taking the reciprocal. So that would be 1 over 2x to the 1/2 power. But again, there's 1/2 power again, right? That is square root. So I can now convert this back to a square root, right? So I end up with 1 over 2 square roots of 2x, which I have to now solve for dx, right? So I've got to solve this for dx. What does that end up being? What now? Oh, you are right. I should punish myself somehow here, okay, right? I forgot the chain rule, okay? So, easy mistake to make, right? Okay, so everybody makes it, me included, but you want to try to avoid that, right? Okay, yes, I forgot the chain rule, which is going to really be to our benefit here, correct? I forgot that this is an expression raised to the 1/2 power. It's not just x to the minus 1/2 power, right? So when you take the derivative of this, correct, okay, you're going to have to multiply by the derivative of 2x, right, which is 2. So let me see if I can squeeze that in here. I need here another factor of 2, right? So we're going to end up here with 2 over 2, which of course reduces to 1. So that's nice. I just end up with 1 over square root of 2x, right? Okay. So if we have a problem like this on the test, there is one like this on the sample test. So if we end up with a problem like this on the test, that's something to watch out for. Remember to watch out for that, right? Okay. taking derivative or forgetting about the chain rule. Okay, well, so now I've got to solve for dx here, right? So is that just du over square root of 2x? Is that it? So, or du times the square root of 2x, something like that, okay? So is it square root of 2x times du? Is that what dx is? Yeah, okay. All right, so now you're on the way here, right? So now we have 1 over, this is u though, correct? But dx is square root of 2x times du, right? Now that's kind of an unhappy situation at the moment, right? Because I still have x, right? So and so sometimes this means your substitution has gone awry and it's back to the drawing board. But in this case, we're still okay because I just have to remember, right? I can solve for square root of 2x back in this substitution, right? It turns out that square root of 2x is u minus 7. So I catch a break there. So I can write this as 1 over u, and then square root of 2x is u minus 7, right? Solve this equation for square root of 2x. You get u minus 7 is square root of 2x, right? And then du. And now you have a much better integral. So you still have some work left to do here, but I'll leave you with, at this point, okay? And again, you're going to think of long division. But you have an easy long division problem here. This is u minus 7 over u. What's the degree of u minus 7? 1. What's the degree of u? 1 is at least 1, so we can do long division there. But it's a really easy long division in this problem. Okay, so now you can do this integral using long division, and then at the end of that, go back and substitute 7 plus square root of 2x for u. Okay, that is, yeah, I can. That's long division. Yeah, that's just I just did it in my head. Okay, yeah, that's what the long division comes out, right? Okay, so look at the example in the notes. It'll finish very similar to the way this one finishes. Okay, all right. Those are very good examples because that y'all chose because they're both in the sample test. Or problems like those are both in the sample test. Okay. All right. Now let's look at. Let's go back. We were in the middle of a problem last time. So I want to finish that one kind of quickly here and then go on to some more examples of, remember we're working with the natural exponential function, which is e to the x power. And so we have kind of a variation on the natural exponential function in this problem. It's not quite just e to a variable. In this problem, it's e to an expression. But this also is considered a natural exponential function. All right. So so remember this this formula here was giving us give us an estimate for the population of California, and this is in thousands. So so if you take the 34,696 and multiply it by 1,000, that would give you the actual population in people. So that's going to be in the millions, right? T here, the variable is, the input variable here is, that's elapsed years from 2000. So we're not using calendar years in this problem. We're counting years from the year 2000, which just makes the numbers a little bit easier to manage, okay, in the problem. All right, so last time we just looked at this. This is really not a, no, it is. I'm sorry. This is a calculus problem, right? We want to know at what rate is the population changing in the year 2020, this year, according to this model, how fast will California's population be changing? And so we knew we had to take the derivative of this exponential function, right, which we did. And then we plugged in 20 for t. That corresponds to the year 2020. And we end up with approximately 409, okay, when we round it off. So this year California's, according to this model, this year California's population is increasing, because this is positive, right, at a rate of 409,000, because these outputs are measured in thousands, 409,000 per year. All right. Okay. Now, now this is the problem that's really not a calculus problem. Really, it says, when will the population reach 45 million? Okay, so to solve that, we're just going to set up and solve an equation. So it's really not, in a sense, a calculus problem. So we already knew what equation we were going to set up, right? Just take your the formula for your population, right, and set it equal to 45 million, right? Because you want to know, when is the population going to be 45 million, and then solve that equation for t, okay? And that would give you your answer, right? We did have to rewrite the 45 million slightly, though, to make it fit the description of the problem. We took the 45 million and wrote that in thousands. So 45 million is 45,000 thousands, okay? So so we had to do that, right, to just make sure we had our units of measure aligned, right? Okay, so that's where we were. We just wanted to solve this equation. Okay, so let's see if we can solve that, right? So what's the basic technique, right, for solving that equation? Ultimately, what are we going to do to solve the equation? So what's the key trick here to solving this equation, to getting t there out of that exponent so you can isolate it on one side of the equation to get your solution? Yeah, the key idea there is, at some point we're going to apply natural log to both sides of the equation. However, you have to be a little bit careful about doing that. Before you apply natural log to both sides of the equation, you need to eliminate this coefficient first, okay? So you have to have e to a power by itself on one side of the equation before you apply the natural log, all right? So this coefficient cannot be there. So, well, it's easy to get rid of that coefficient, right? Just divide both sides by 34,696, right? So, so that's the first step. That's easy step to forget. So, just wanted to remind you of that. So we have 45,000 divided by 34,696 is equal to e to the 0.0097 times t, right? Okay. And you really don't have to, I guess, but if you want to, you can go ahead and use your calculator to get a decimal approximation for 45,000 divided by 34,696. But actually, you can really skip that step first and go ahead and apply natural log to both sides, okay? It's just going to give you kind of large numbers to work with. So if I skip writing down a decimal estimate for this fraction, I would have natural log of 45,000 over 34,696, right, is equal to natural log of e to the 0.0097t, right? And these functions are inverses of one another, right? So what does that mean? They cancel each other, right? Okay. So you end up on the right-hand side here with just 0.0097 times t, right? Which is easy to solve now for t, right? Just divide by 0.0097. So there's your answer in exact form. Okay. This is exact form, not decimal form, right? T is equal to the natural log of 45,000 over 34,696, and then take all of that and divide by 0.0097, right? Okay. Now there you really need a calculator, right? Okay, because who knows what that number is? I have no idea. What does it turn out to be? Hope it's not too big. Round off to a, well, no, maybe one decimal place is enough. Does somebody want to do that for me? 26.8? Oh, great. Okay. So that's not too far in the future, right? So in sometime in the year 2026, right, if this model is correct, remember this is elapsed years, right? So sometimes in the year 2026, sometime between 26 and 2027, right, the population of California is going to hit 45 million. Okay, wonder how accurate that is. I don't know. We can look up the population of California pretty easily. All right. Now let's look at, so we did differentiation of exponential functions. That's so easy, right? Because exponential functions are essentially their own derivatives. So very easy to differentiate exponential functions. And so antiderivatives are going to be equally easy. If you just have antiderivative of e to the x, the antiderivative of e to the x, just plain old e to the x, that is e to the x, okay? So that's very nice. So easy to integrate e to the x. If you have a little bit more complicated natural exponential function where you have e raised to an expression, okay, e raised to an expression, not just x, but an expression involving x, then you're going to need the derivative of the expression in the integrand. But if that is multiplied into the integrand, then when you antidifferentiate here, right, when you find the antiderivative, you just get e to the expression plus a constant, okay? All right, so, but be careful about this. If you're finding the antiderivative of natural exponential function, that means base e, a natural exponential function, then if this exponent is an expression involving x, you need to have the derivative of the expression in the integrand before you can integrate, okay? So if that appears to be missing, you're going to use substitution. You're going to use substitution and hope that good things happen, all right? Okay. Here is kind of the substitution version of this rule. If you let u represent this expression, right, that's in the exponent, then this rule says, oh, if we have e to the u, right, du, the derivative of that expression, then that integrates as just e to the u plus c. All right, so let's try one. And we already started off with a little bit more complicated one, right? We have e to the 3x plus 1. So there you do have a natural exponential function because you've got a function, right, that's base e, okay? And but the exponent there is not just x. It's an expression involving x, right? Okay? So a little bit more complicated natural exponential function. All right, so to integrate this, we're going to use substitution. All right, we're going to use substitution. And we're going to substitute u for the exponent. Okay, so I'm going to let u be 3x plus 1. And I'm going to show you what's going to happen there. All right. All right, so you just go through the substitution process. So this is all very familiar to you, right? What's the derivative of u here? 3. So we solve that for a dx, right? So it looks like we get dx is what? Du over 3, right? So let's substitute that then. So I have the antiderivative of e to the u, and then dx is du over 3, right? But that over 3 now is a constant, so I can factor that out. So that's exactly what I'm going to do. So I'm going to factor that out, and I'm going to write that as 1/3 e to the u du. But this now is easy to integrate, right? What is the antiderivative of e to the u du? That's e to the u, right? Okay. See here, you just have e raised to a variable, right? And so its antiderivative is just the same thing, e raised to the variable. So you just get, as your antiderivative, e to the u. Don't forget to add your constant on. Now you fix the substitution, right? What was u? That was 3x plus 1. And there you're done, see? So notice in the antiderivative, indeed, we repeated the e to the 3x plus 1. But notice what kind of showed up a little bit unusual there is the extra factor of 1/3, okay? Shows up there. All right, let me show you let me show you another way of thinking about what we did with the substitution. See, look at the antiderivative. I said, let's see, if you have e raised to an expression, in order to integrate that, you need to have the derivative of the expression, right? But what is the derivative of 3x plus 1? 3. Unfortunately, I don't have a 3 here, you see. Okay, I do not have a 3, right? So that if I had a 3, then I could immediately find the antiderivative. So here's how I compensated for this. I don't have a 3, so I'm going to put a 3 there. I'm just going to put in a 3, okay? But, of course, if I just put in a 3, I've changed the problem. So I don't want to change the problem. But I can undo that 3 by, at the same time, multiplying by 1/3, right? Because what is 3 times 1/3? 1. So if I put a 3 here, I'm going to put a 1/3 outside. 3 times 1/3 is 1. So I really haven't changed the problem. But I certainly now have it in a form that I like. Because, see, here I have e raised to an expression times the derivative of the expression. So what's the antiderivative, I said? You just get what? This, right? Just e to the 3x plus 1. Yeah. But remember, what's left over there that I had to insert? The 1/3, right? Okay. So the 1/3 is left over. So there's another way of thinking about attacking the problem. That all sort of happened, that process that that trick there of adding the 3 and multiplying by the 1/3, that all sort of happened by doing integration by substitution. All right? But you can really avoid thinking of integration by substitution if you think about it just right. Okay. All right. So same answer either way. All right. So let's try the next one. All right. Oh, well, it looks like I'm going to let y'all try the next one. So that's good. But let me get you started here, okay? Here's how I would sort of think about the problem. All right. So look, I have, first thing I want to look at there is, I have e raised to a expression, right? Okay. So I'm sort of thinking, yeah, I know how to find the antiderivative of that, because the antiderivative is probably going to be e raised to that expression, right? Okay. But that expression is not just plain x. That's minus x squared. So if I want to immediately find the antiderivative, if I want to immediately integrate without any work at all, what would I need multiplied in here? You need the derivative of this, okay? See, if you have the derivative of the exponent multiplied in to your integrand, you can integrate instantly, all right? The antiderivative will just be e to the minus x squared, okay? But what is the derivative of minus x squared? Minus 2x. Is this minus 2x? Unfortunately, not, you see, okay? It's close, really close, right? Okay? But it's not minus 2x, see, all right? So, unfortunately, I cannot just immediately here say, oh, I know what the antiderivative is, all right? But we shouldn't give up, all right? This is where I'm going to switch to substitution, okay? All right, so what will I substitute? What's my typical strategy in these natural exponential functions? What will I let u be? The exponent, right. So let u be minus x squared, okay? And now try that substitution, and like in the previous example, try that substitution and see what happens, okay? Hopefully good things will happen there, all right? Let me put the other problem on there so y'all can see what we did. Oops, that wasn't the... Let me go back to the original problem. There was the original example, prior example. So see if you can follow that one, same steps, and find the antiderivative of 5x e to the minus x squared. Okay. All right. So Taylor and I will assist you as needed here with this one. If I can tie my shoe. Did you get the substitution right? Yeah, that looks good. So go ahead and substitute. So did you take the derivative there? Yeah. So what is that du dx there? Yeah. Now solve that for dx. Solve that equation for dx, and then plug that in for dx there. Okay. And then of course you plug in u for the minus x squared in the exponent, right? All right. So what are you doing here? So you get minus 2x. All right. So you got to this point. Now what did you do?
I'm not sure what to do because but what I did.
Well, yeah. So you're going to do a little bit of algebra here, right? Okay, very little bit of algebra because, and this is really what you're looking for. Here you have an x multiplied in, but here you're going to divide by x. So what happens to these x's?
They cancel.
They
out.
cancel. That's what you're hoping for, right? Okay. And now you have 5 halves, right? 5 over 2, constant. So what can you do with that? Pull it out, right? Okay. Exactly. That looks nice. Is that where did the minus sign was here, right? Okay. So that's what we got a minus sign there for. Okay. All right. I wasn't sure if there was supposed to be a minus sign there. What did you get? Right. Nice. Okay. See if you can do that one. If you can do that one, you can do a lot of good things there. Right. Yeah, perfect. Yeah, you're just on the right track now. And what about the 5 and the minus 2?
Yeah, I'm about to
Yeah, you're going to put it out. That's exactly right. Yeah, you're going to take it out. All right. So
Am I on the right?
Yeah, you're on the right track, but you didn't write this down the same way. This is not this. What happened to the e to the minus x squared? That's still in the that's still in there, right? Okay, except it's e to the u now because you're substituting u for minus x squared, correct? But now at this point, some things are going to cancel. Okay, did you finish there?
Yeah.
Right, perfect. That is right. See how easy that is? Oh, you were saying hello to me earlier. I didn't recognize you, so.
I was on what's up.
Okay, yeah, I know. I have so many students, it's hard for me to remember. All right, perfect. Wow, see, yeah, so y'all are doing that so easy, I think. What happened there? Yeah, you're in great shape. Now, what happens to those X's?
Since they're over each other,
They cancel, right? See, here you're multiplying by X, and here you're dividing by X's, so the X's cancel. So and that's exactly what you want, right?
Yeah.
Just scratch them out. Yeah, yay, that's what you want. You want the X's gone.
Right.
Now, what about the 5 over the minus 2? See, you have 5 in top and minus 2 in the bottom. What can you do with that?
Take out.
Take it out, right, okay? You take it out, exactly. Done? All right. You see all these people? Oh, okay. All right. Ooh, y'all did that one nicely, okay? That's going to be a happy situation on the homework if y'all can repeat that a happy situation on the test if y'all can repeat that sort of problem on the test, okay? Just a key thing to notice there, right, is, here we have e to an expression. So I know e to an expression, probably going to integrate that as just e to the expression, right, with just a few little extra steps, right, thrown in, like maybe this substitution for the expression. So when you take du dx here, right, you got minus 2x, right? And then when you solve for dx, it was what? That turns out to be du over the minus 2x, correct? And now we substitute there, so we get 5x e to the, now this is called u, right? And then dx is du over minus 2x. And now what you always want, what you're always hoping for in substitution at this point is you're hoping for some cancellations. And we got that right here. The x's cancel out. and the 5 over the minus 2, notice this is 5 over minus 2. This 5 is in the numerator, and this negative 2 is in the denominator. You can factor that out as minus 5 over 2 in front. And then that leaves you with e to the u du, and that's exactly the form you need it in to integrate, right? So you have minus 5 halves e to the u, and then plus a constant, right? Because this thing just integrates as itself, right? E to the u just integrates as itself. So essentially you're done, right? Except you just have to undo your substitution. So you get minus 5 halves e to the minus x squared, and then plus this constant. All right, I've got a couple of these here I have on video. So in your homework for this section, this is the 5.3 homework, I think, or 5.4 homework. So there are links in the homework description or the instructions at the top right to these two videos. But let's let's just start them, okay? So how would we start this one? First thing to notice, that's e to an expression. So I'm thinking, I'm hoping I can integrate this as, just e to the expression, right? Okay, with that little bit of extra work. But we do have a little bit of extra work, right? Because my expression is not just plain x, right? The expression in the exponent is not just plain x, it's 1 over x. So what would I try to get started here? Substitution, right? So substitute for u for 1 over x, which, by the way, is x to the minus 1 power. And then what is du dx? Don't integrate, but differentiate. What's du dx? How do you differentiate this? Bring down the minus 1, right? So you have minus x raised to what power now? Minus 2, right? Okay, which is minus 1 over x squared, right? Because minus 2 exponent, you can write that as a reciprocal. That's very promising start to our substitution, because why? Notice that is also in the integrand. So, I'm really happy. All right. I'm thinking maybe this substitution is the right one. Okay. All right. So, don't forget, you got more work here, right? You have to solve for dx and then substitute for dx, correct? Okay. But I have a good feeling that something good's going to happen here. All right. Same thing in the, so again, we have this all on video. Same thing in the next example. Don't get dazed here. Don't get snowblind because of the trig functions. Okay, so don't let them intimidate you. We have some trig functions here, but more importantly, we have this exponential function, right? We have e to an expression. It's just that this time the expression involves a trig function. All right, so the first thing I'm looking at is the e to the expression, not the sine, not the cosine. I'm looking at the e, okay? And I'm thinking, I hope I can integrate this as an exponential function, making a substitution. What substitution, of course? Yeah, let u be cosine of x. Let u be that exponent, right? And what is the derivative of cosine of x? Be careful. Negative sine of x. And again, I get a warm feeling because that sine of x is showing up here in my integrand, right? So I have a feeling that I'm going to be able to cancel the sine of x once I solve this for dx and substitute, okay? So I'm thinking, wow, I'm off to a good start, okay? I'm off to a promising start with this problem. All right, so you can see the rest of that, but you can probably finish it here pretty easily in the video of this. All right, okay, so let's take a few minutes now. So let's take 5 minutes or so, and then we'll come back. And I think I have a couple, or maybe one only, definite integral. We've been doing a lot of indefinite integrals. Let's look at a definite integral, but that's almost the same thing, right? Okay, let's resume. I've got a definite integral problem. So I'll go through this one. This one's very straightforward, I think. And then we have one last example, but again, this one is on video. So so that's the third video, I think, in your in the homework for this section. All right, so let's do this pretty simple definite integral. So we're trying to find the definite integral of e to the minus x, so that's almost e to the x, right, from 0 to 1, okay? And so clearly, well, we have to find the antiderivative of e to the minus x, right, and use that to evaluate the definite integral at the limits, right, of integration. But this is not quite e to the x, it's e to the minus x, so we do have to do substitution here, but it's a pretty easy substitution. So just let u be minus x, right? And then du dx is very simple, right? It's just minus 1, okay? Right? The derivative of minus x is minus 1. So when you solve that for dx, it looks like you'll get minus du, right? Okay? Du over minus 1, which is the same as minus du. So so we can rewrite this definite integral, right, this way. E to the u, and then here a minus du. There's there's one thing I've got to point out here that I'm being a little bit sloppy about in doing this definite integral. When we change the variable here from x to u, these limits of integration are in terms of x. So technically, we should also change the limits. You don't have to do this for an indefinite integral, but for a definite integral, we should technically also change the limits of integration to correspond to u, okay, not x. But I'm going to skip that step because immediately, right, after we find the antiderivative, we're going to change the variable back to x, all right? So that's just a little bit of unnecessary work in this case to change those limits of integration. But when I write this equals this, technically that's not correct, okay? All right, those two things do not quite equal. They would equal if I had switched the limits of integration to correspond to u, all right? Okay, so, but let's proceed here nevertheless. So look, notice this is minus du, right? So you have a factor here of minus 1, and that is a constant, so we can factor that out. So I have minus here, this definite integral of eu du, right? And now we know how to find the antiderivative of this quickly, right? That is going to be, well, what is that going to be? E to the u, right? Okay, just e to the u. And our limits of integration right here are 0 and 1. So notice here we have already, notice here, right, we have already carried out the integration, right, so the integral sign is missing, and there's our antiderivative, but I need to evaluate that at 0 and 1, right? But before I actually evaluate 0 and 1, right, we need to switch the, undo the substitution, correct? What was u equal to, though? Negative x, right. So I get, and don't forget about this minus sign, right, that's hanging around. So I have minus, and then e to the minus x, and now that's evaluated from 0 to 1. Now the limits of integration are correct again, okay, because I've switched the variable back to x. All right, so let's see, what would this be? Well, plug in 1 there, right, for x. So you get e to the minus 1, right? Okay, and then plug in 0 for x, so you get minus e to the minus 0 power, which is just 0, right? So First, just plugged in 1, then I plugged in 0, right? And remember, you take the difference. Don't forget, this minus sign is also there, though, because of the minus sign we had outside of the integral. All right? Well, let's see. What is e to the minus 1? Yeah, no, it's 1 over e, right? Remember, when you have a negative exponent, that means take the reciprocal. So e to the minus 1 is 1 over e, all right? Now, you can use your calculator to get a decimal estimate for that, but before we get to getting decimal estimates, just write that as 1 over e. So I have minus and then 1 over e. Now, what is e to the 0th power? That is 1, right? So any non-zero number to the 0th power is 1, including e. Remember, e is a number. So e to the 0th power is 1. So you have minus 1 over e minus 1, and that, if you distribute this minus sign, that's going to be 1 minus 1 over e. So there is your answer there, okay? 1 minus whatever 1 over e is. Okay. So that's an exact form, and then you can use your calculator to get a decimal estimate for 1 minus 1 over e. Okay. All right. So there's your introduction to the natural exponential function and its derivatives and its integrals. And pretty straightforward, right? The natural exponential function is a pretty easy function to work with, okay? Now, let's switch our focus back here, though, a little bit to logs again, so logarithmic functions. So we introduced, right, and have been using the natural logarithm function. And actually, that was the students are sometimes surprised to know this, but the natural logarithm function is actually the first logarithm function that was actually used in practice. Okay, and so and that was developed in Europe in the 1500s or sometime in the 1500s. But there are logarithm functions of other bases other than e. Okay. And so two of the ones that are that you use most frequently, okay, are log base 10. This is called common log, okay, not natural log, but common log, and that's often abbreviated to just log without the base. So if you see the word log without a base, that means log base 10. So on your calculator, you have a log key that is log base 10. All right, ln is log base e, right? Okay, but log written without a subscript is log base 10. So that's a frequently used logarithmic function other than the natural logarithmic function. All right. The reason that we use that a lot is our number system is base 10. Okay, so that makes the common log useful because our number system is base 10. Another base that is frequently shows up in practice is log base 2. Okay, that's called the binary log. All right, I like to abbreviate that as LG. All right, so without a base, without a subscript there. Okay, so if you see me write LG, that means log base 2, okay? You won't have an LG key on your calculator, however, okay? So usually calculators just have a log and a common log and natural log, all right? But this is another important log because computers, right, encode information as base 2 numbers, not base 10 numbers, and so log base 2 is useful for that reason, okay? All right, but you can have you can define a logarithmic function for any base at all. Okay, so any number that you want to use as base, as long as it's positive, you can create you can define a logarithmic function for that base. All right, but these are the ones that you'll see 99% of the time. Okay, log base 10, log base 2, or the natural log, log base e. All right, now how do we define these? How do we define these log functions for other bases? Okay, well, here's the here's the algebraic way, not the calculus way, but here's the algebraic way of defining logarithmic functions for other bases. So you're familiar with logarithms to different bases, and it's almost certain that you had them defined similar to this, okay? So if you write that y is equal to log base b of x, so that could be log base 10 of x, or that could be log base 2 of x, or that could be log base 7 of x, because you can, make a log for any base, right? That's true if and only if when you take the base and raise it to the y power, you get x back again, all right? That's how log functions work, okay? So if log base b of x is equal to y, that means that b, the base, raised to the y power is going to be equal to x. And that definition allows you to understand how log functions are evaluated, okay? So for instance, what would LG of 16 be? That is log base 2, right? Okay? That's log base 2. So how would we compute log base 2 of 16? What are we looking for? Log base 2, let's write it down. So log base 2 of 16, right? Log base 2 of 16. If we call that y, what do we know about y? What does this definition say? It says what? Take the base and what? Raise it to the y power, and what are you supposed to get? Yeah, in this case, the 16, right? So 2 to the y power is supposed to be 16. Well, what power of 2 is 16? 4. So you know that log base 2 of 16 is 4, correct? Okay. What about log of 10? Log of 10. So log without a subscript means what base? 10, right, okay? That's called common log. So to read that off a page, you would say common log of 100, common log of 100. What's common log of 100? 2, right, yeah, okay. That is 2. How do we know that? Because what? 10 squared is what? 100, right, okay? What's the binary log of 1/8? Binary log of 1/8. So remember, binary log is log base 2 of 1/8. So let's call that y until we figure out what it is. But what do we know about y? If you take 2 and raise it to what? The y power, what are you supposed to get? 1/8. What power of 2 gives you 1/8? -3, exactly right. Yeah, it's -3. 2 to the minus 3 power is 1/8, right? You can just check that, right? 2 to the minus 3 means 1 over 2 cubed, but 2 cubed is 8. Okay. What about log? Common log of 1/10? -1, right? Okay. Because 10 to the minus 1 power is 1 over 10. That's 1/10. Okay. So that's the definition, right, that you probably learned in an algebra class for evaluating logs of bases other than E. Okay. All right. And of course your calculator is really good at doing these calculations. Well, for base 10 especially, correct? Right. Now, however, so that's the algebraic way of defining logs to other bases. But here's the calculus way of defining logs to other bases. All right. So remember, we already defined the natural log function, correct? So we started with the natural log function way back, right at the beginning of the course. Remember, we created the natural log function, and so here in calculus is the way we create the other log functions here. All right. We derive them from the natural log function. So if you want to compute a log of a base other than E, okay, then according to our definition, you calculate that by computing the natural log of the number and then dividing by the natural log of the base, or multiplying by 1 over the natural log of the base. Okay. That's the calculus definition for other logarithmic functions. Notice they all are built around the natural log function. So what's the calculus definition of common log? log of log base 10. According to this definition, what would that be? 1 over what? 1 over natural log of 10 times the natural log of x. Okay? So see, you compute a common log of a number by taking the natural log of the number and then dividing it by the natural log of 10, or multiplying it by 1 over the natural. Wow, I wonder if that's correct. Let's check that. Let's check that up here, because we already knew that log of 1 over 10, right, was minus 1, right? According to this definition. Let's see if that works, but we'll need our calculator to help us here. So let's see if that works using this definition. So according to this definition, how would we calculate log of 10? That would be, so log of 1/10 would be what? 1 over the natural log of what? 10 times the natural log of what? 1/10? All right, so you got to help me here. Try that on your calculator. Try computing the natural log of 1/10, 0.1. Try computing the natural log of 0.1, and then also compute natural log of 10, and divide them by each other, and I hope they come out to be minus 1, but is that going to happen? What does your calculator say is the natural log of 1/10, approximately? What's natural log of 0.1 on your calculator? Yeah, natural log of 1/10. -2, that sounds a little bit big to me. -2.3? Okay, so well, maybe that's right. So minus 2.3, are there some other decimal places there? 0.302. 0.302?
You want me to keep going? Yeah.
Okay, well, let's leave it at that. What is the natural log of 10? Is that 2.302? Ah, right. So when you divide those, what are you going to get there? -1, right. Okay. Exactly what we were hoping to get there, right? Okay. Now, that's just a little bit of a verification. All right, but at least in that situation, those two definitions agree, right? Okay, or at least this definition gives us what we were expecting to see, right? Okay. All right. So, well, obviously, right? It must be the case that these two definitions are equivalent. All right. So, if you compute a log base b using this definition, you will get the same thing if you compute log base b using this calculus definition for the number. Okay, they are going to turn out to be equivalent to each other. All right. Now, why might this definition be more useful to us? Because this is the one you learned in algebra. All right, and this is very useful in algebra. But why might this definition of log functions, other than natural log function, why might that definition be better for us? Well, because we're in calculus, right? And what are we going to want to do with these log functions with different bases? What do we do with functions in calculus? What? Integrate them, but also what? Differentiate them, right? Yeah, we want to be able to integrate them and differentiate them, okay? Right? But this definition will make it easier for us to integrate and differentiate because this definition, again, is based on the natural log function, and we already know how to do what? Well, we already know how to at least differentiate the natural log function, correct? Right? Okay? By the way, we didn't learn how to integrate the natural log function. We did not do that yet, all right? So that's coming up, okay? But at least we can differentiate the natural log function, right? That's an easy derivative. So that means that using this definition, we're also going to be able to differentiate log functions of other bases, okay? All right, so that's why this definition is useful to us. And in fact, I'm going to show you the rules here, okay? But I think before I get to the rules, let's solve a couple of easy problems. All right. So these are really algebra problems. Back to solving equations. All right. So let's start with this first equation. 3 to the x equal 1 over 81. We could almost solve that using just inspection. Okay. I think you just look at that and get the solution. But let's see if we can do it a little bit more systematically. So that when we encounter maybe a harder equation like this, we don't have to rely on just inspection. All right. So 3 to the x power equals 1 over 81. So if that were e to the x power, right? Okay. Of course, how would I go about solving that? Yeah, you would apply the natural log to both sides, right? Because the natural log is the inverse of e to the x, right? Okay. So do we have an inverse for this exponential function? This is not the natural exponential function because the base is not e. All right. Okay. Well, guess what? We do. Okay. The log base 3 function is the inverse also of the 3 to the x function. All right. So these exponential functions and logarithmic functions of different bases, they are inverses of one another, just like the natural log function is the inverse of the natural exponential function. So to solve this equation, we can apply log base 3 to both sides. Okay. So let's try that. So I'm going to write log base 3 of 3 to the x power is a log base 3 of 1 over 81. All right. And so what happens here? Yeah, they cancel because these two functions are inverses of one another. Just like log base e is inverse of e to the x, log base 3 is inverse of 3 to the x power. So on the left-hand side, you're just going to get x, and on the right, you have this quantity, log base 3 of 1 over 81. All right. Now, I think you can evaluate that just by inspection. You can evaluate that just by inspection because all you have to think about is, right, going back to your algebraic definition of log base 3, right? Log base 3 of 1 over 81 would be the power of 81 that gives you 1 over 81, correct? What power of 3 is 1 over 81? Is that an easy one to discover? What now? It's negative 4, right? Okay. Yeah. 3 to the minus 4 power is 1 over 81. Okay. Because why? 3 to the first power is what? 3. 3 squared is 3 cubed is 27, and 3 to the fourth power is 81. 3 to the positive fourth power is 81. So that means 3 to the minus fourth power is going to be 1 over 81. So this one we can figure out just by looking at it, right? Okay, that the answer here must be minus 4. But if you can't see that from looking at it, you have other techniques you can use. What is the calculus definition of log base 3? All right, so what's the calculus definition, what's the calculus method for calculating log base 3 of 1 over 81? Y'all just told me that. What? We would do what? 1 over natural log of what? 3, right. 1 over the natural log of 3 times what? Times natural log of what? 1 over 81, correct? Okay. Now, of course, you look at that and you're thinking, I don't know what the natural log of 3 is, right? I don't know what the natural log of 1 over 81 is, so how does that help me? Well, you don't know what it is, but what does know what that is? The calculator, right? Okay, so here you can use your calculator, you see, okay, and also calculate here that the answer is going to be minus 4, all right? So, see, this calculus definition allows you to apply your calculator to this. All right. Let me show you yet another way of solving this equation. Very similar, actually, to this. All right. Look, we solved this equation by applying log base 3 to both sides of the equation, because log base 3 is the inverse of 3 to the x power. But you can also solve this equation by just immediately applying natural log to both sides. Why does that also work? Okay, so why does this also going to give me solutions? Look, you cannot cancel these two functions, though, because they are not inverses of one another. This is log base e, and this is base 3. So you cannot immediately cancel those functions. But you can use a property of logarithms. What's the property of logarithms when you have logarithm of a power? What can you do? You can bring the exponent down, right? So see, notice, you can bring the x down. So you get x times natural log of 3 is equal to the natural log of 1 over 81. And now you can finish solving that just by dividing both sides by natural log of 3. Notice what you get here is this solution, right? You get natural log of 1 over 81 divided by natural log of 3. So there's three ways of solving that equation. Okay? All right, how am I going to solve this equation? This one's really easier. Let's go back to our inverse idea. Let's go back to our inverse idea here, okay? So this is log base 2. Remember, I sometimes write that as LG, log base 2. That's binary log, so that's a log we use frequently, all right, especially for those people who are going to be computer programmers, log base 2. So what would be the inverse function of log base 2? To the power, right, 2 to the x, correct? So I'll just take 2 and raise it to both sides of this equation, okay? So write this equation down. But what happens here on the left-hand side? Cancel, right. Those are inverse functions. So you get very easily the solution here, right? X is 2 to the minus 4th power. What's 2 to the minus 4th power? 1 over 16, right. That's 1 over 2 to the 4th power. 2 to the 4th power is 16. So immediately there, you get the solution. Okay, so that was pretty fast. Can y'all think of another way of solving that? I can. Let me see if this works. So I had originally log base 2 of x is minus 4. But what's the calculus definition of log base 2 of x? What is it? 1 over what? 1 over natural log of 2 times what? Times natural log of what? X, right. So write down this equation. And now let's see if we can solve that one for x. So first, let's get rid of this number by multiplying both sides by natural log of 2, right? Can I do that? Multiply both sides by natural log of 2. So I get natural log of x is equal to minus 4 times the natural log of 2. And now how can I solve that equation? Do what? Raise e, right, to both sides. And you get this strange number here, right? X is what? E to the minus 4 times the natural log of 2. Apparently, that's going to be how much? What did we say the answer to this was? 1/16? All right. So apparently, when you take e and raise it to minus 4 times the natural log of 2, you're going to get 1/16. Okay? I might try that on the calculator and see if that comes out to be 1/16. What is 1/16? 0.0125 or something like that. Okay? Or is that 1/8? Maybe that's 1/8. All right. So there's yet another way of solving that equation. All right, so those are just algebra problems, but let's look at our the things from calculus that we're interested in. So here's actually now how we differentiate and integrate with logs or exponential functions other than base e, okay? So we've been integrating e to the x power, right? We've been differentiating e to the x power. We've been differentiating natural log, correct? We did not integrate natural log. We didn't integrate natural log yet, right? But we know how to differentiate it. Well, all right, so here are the analogous rules for, the similar rules for other bases, okay? So if you want to differentiate b to the x power where b is something other than e, okay, that's an easy derivative. Just, you're going to keep b to the x power. Kind of expected that, right? You're going to keep b to the x power, but you have to multiply in the natural log of b, okay? So the natural log of b has to get multiplied in there, all right? That's not the chain rule. That's not the chain rule, okay? That is just the way exponential function with bases other than e, that's just the way they differentiate. If you do have a base raised to an expression, not just plain x, but an expression involving x, the derivative looks kind of the same, right? You repeat the b to the expression, you multiply in the natural log of b, but now this is the chain rule, okay? So you also have to multiply in the derivative of this expression. So if your exponent is something other than just plain x, don't forget the chain rule like I did a moment ago. You must multiply in the derivative of the expression, okay? All right, so that's differentiating exponential functions, not base e. What about integrating log functions, not base e? All right. Well, if you not integrating, but what about differentiating log functions other than with other bases? So if you want to differentiate log base b, so like something like log base 10 or log base 2, you still get 1 over x, right? Just like you would if you differentiated natural log, but also in the denominator, you have an extra factor here. It's the natural log of the base. So notice natural log of the base is showing up here over and over again, right? Okay. If you have log of something other than x, a little bit more complicated than x, right? Same derivative. You get 1 over the natural log of b, right, times the expression. But then don't forget the chain rule. So you have to multiply in the derivative of the expression, okay? What about integrating something other than e to the x? Very easy, okay? It's sort of similar to integrating e to the x. You just get b to the x back again, but you've got this one extra factor you have to divide by the natural log of b. So remember, if you're differentiating b to the x power, you multiply by the natural log of b. But if you're integrating b to the x power, it's the opposite. You divide by the natural log of b. All right? And then finally, the more complicated version of that is if you're integrating some base other than e to an expression, well, you can do that just like in Rule 5, but remember, you must have the derivative of the expression multiplied in. Well, so situations like this are usually going to require you to use substitution. All right, so this is kind of integration by substitution, this Rule 6. Okay, so very straightforward to differentiate log other than b, right? Or differentiate exponential functions other than base b, or integrate exponential functions other than base e. Ooh, well, we have time for a couple of examples here, but they're so easy because they're so much like natural log or natural exponential function. So what if I want to differentiate 2 to the x power? So that's almost the same as e to the x power, right? Almost identical. E is about 2.71828, right? So e to the x is 2.71828 raised to the x power. Here we just have plain old 2 raised to the x power, but very close, right? So how do I differentiate this? So, by the way, you can write this down as dy over dx. That means the derivative. Or you can also write y prime, right? That means derivative. These are just different notations for the same thing. This is the more modern notation, and this is the sort of the old-fashioned notation from the beginnings of calculus, but they both mean the same thing. They're both useful, by the way, in different situations. Well, what is that derivative, though? So when you differentiate an exponential function, what you do always get the exponential function back again, okay? So you're going to get 2 to the x, but since this is not base e, what do I have to also multiply in here? ln of 2, right, okay? That's not the chain rule. That's not the chain rule. That's just the rule, part of the rule for differentiating bases other than e. All right, so now this one's going to involve the chain rule. So what's the derivative here? 2 to the 3x power. So what's y prime in this case? So you can always get the first part of this. So you can maybe always get 1 point on the test, right? Because you always know this is going to start how? Yeah, you're going to repeat 2 to the 3x, right? But now we have some extra factors. Natural log of what? 2. But one other thing. What do I have to multiply in here also? What? 3. Right. Okay. That's the chain rule. Because the derivative of 3x is 3. So you didn't need that up here because this is just x. X's derivative is 1. So there's no sense in multiplying an extra 1 here. But 3x's derivative is 3, right? So you need to write that down. So there is your derivative, okay? What about log there then? All right, so we want to differentiate log. This is log base 10 because no subscript is written. So I want to differentiate log base 10, common log of cosine of x. So what's the rule for that? So you can write that as y prime or dy dx. How do we differentiate logs? Yeah, you get 1, so you 1 over, right? So you get 1 over cosine of x, and then what else is going to have to get multiplied in here, though? Natural log of 10, that's right. That goes into the denominator with the cosine of x. But there's one other thing now that comes in here, not in the denominator. So what's the other thing that goes in here? It's the derivative of cosine of x. That's the chain rule, okay? What's the derivative of cosine of x? Minus sine of x. So are y'all going to remember that? Yes, you must here also multiply in minus sine of x. Because this is not just log of x, this is log of cosine of x. So its derivative must be multiplied in. All right, so how does that simplify? We can simplify that a little bit, because what's minus the sine over the cosine? What's that better known as? What? Tangent. So that's minus the tangent, right? This is, if I can get my pen to work, this is minus the tangent of x, and then, but don't forget you have that natural log of 10 there, right? So this is minus tangent of x over the natural log of 10. Okay, well that's a good place to quit because I have a video for this one. This one's a little bit harder though, right? Okay, a little bit harder. This is log base what? 2, right. So we're trying to differentiate this. So you know you're going to take the reciprocal of this, right? And then, so that means you're going to flip this fraction. That's going to be part of the derivative. But what else will be in the derivative? Well, you have to multiply in the natural log of what? 2, right? Because this is not log base e. And then, ooh, ugly. I have to figure out what's the derivative of square root of x over x plus 5. Yuck, all right? That's a nasty derivative, but that has to go in there, okay, at the end. All right, well, so there's a video for that example. Okay, in the homework for this section, which is 5.5, I believe. Okay, so we're done for today, right? So don't forget to finish your homework. I don't want to have to be sending you emails scolding you for not doing your homework. So finish your homework, right? Okay? And I'll see y'all Monday.